So again, considering our typical exam questions on our AC machines, the first part of our synchronous machines, the part of AC generator, we are given here on question number 4, which was 4.1. This is the second paper of our November 2024 exam, which is the replacement paper. So 4.1, you were given to explain the term armature reaction as applied to alternators. So we can have this definition, guys. So your definitions, you answer the way that you understand, but that is the influence of the stator ampere turns on the value and distribution of the magnetic flux in the air gaps or in the air gaps between the poles and stator core. So we are simply saying this whole part is the influence. It is the influence of the stator. So there we are talking of what? The stator ampere turns. So be having ampere turns on the value and distribution. And what? Distribution, that is distribution of the magnetic flux in the air gaps. So this is taken in the air gaps between, that is in the air gaps between the poles, and the stator. So we are dealing with the stator core. So that is the major part, guys, that you need. I just want you to go through your revisions, explanations of the definitions, right? But as a major part of our calculation here, 4.2, we are given, not to say that part is not important, but know your theory, guys, all right? So 4.2 we are given in this case. This is a 3-phase. We are dealing with a 3-phase star-connected alternator. So according to our information, that's according to the data that we are given, we have 3-phase star connected there. All right. So that's a 3-phase. All right. Then it's what? Star connected. Okay. So that is what we have in that case. Are we together? In this case, star connected. So remember, when we are given this star connection delta, we are dealing with what? 3-phase. They can sometimes leave this part of the 3-phase, then they just say star connected. You know that you are dealing with what? 3-phase. So this alternator in open circuit is required to generate a line voltage of. So there they've actually specified the line voltage is, our line EMF is what? 3,600. Whether they do not specify like this, you must know that the open circuit that you're given is the line voltage, unless it is being stated otherwise, but that is what? Your line voltage. You also have the frequency and the speed from there. So that's our frequency. In this case is what? Is 50 hertz. And the speed is given 500 revs per minute. So if you see this part, I combine it because it has to play a role. Once you're given frequency, guys, and the speed, there will be something there, number of poles. So in this case, because we have it as a question here, I'm not going to focus with it because they're asking us here. But we're supposed to, once you see this, I told you guys, once you're taking this information, once you see, calculate the number of poles from there. But here, because it's already asked, so let us just leave it. All right. Then we are given, assume all the conductors per phase are connected in series and that poles are full pitched. Full pitched. We know this from our N5. our pitch factor will be equal to 1 because it is what? It is full pitched. Remember that part when you refer to the pole pitch, guys, the full pitch, it will be 1. All of it. So there, that is the what to be given, the distribution factor. All right, this time we are given 0.96. So we're also given the distribution factor of what? 0.96. This is what we have. All right, and also from here, remember it's a star connection. So let's just calculate our phase value. Remember I said here, the phase value can be calculated, our induced EMF per phase, from what? Line voltage over the square root of 3. So we have the line induced EMF there, 3,600 over the square root of 3, which is at open circuit. So that was going to give us 2,078.461 volts. All right. And also, according to this, we are not given the form factor. Even later on, you are not given anything about the form factor. So you take your form factor to be equal to what? 1,11 in case you are going to need it in your calculations. You're not given that. So that was it, guys. Let us quickly check our question 4.21, the number of poles. So, like I said, from frequency and what and the speed there, we can use this to calculate the number of poles. That is actually, let me just use it here, guys. I'm just gonna use it this space here, 4.21. Remember, we can manipulate from what? From n, the speed, n, which is equivalent to 60F over what? 60F over P. So we can have P from there, cross multiply, then divide. So it's going to be 60F over what? Over N. That's 60 times our frequency, 50, over the speed in revs per minute, which is what? 500. It must be in revs per minute. So we are going to have the pole, the pairs in this case of our poles. All right. So this was going to give us what? 6. That's 6 pairs. So therefore, how many poles do we have? From 6 pairs, the number of poles. So number of poles, I'm just going to write in short. The number of poles, remember pair, you are working with 2 things at the same time. So that's 6 times 2, which is going to be 12 poles. So 6 times 2, that's 12. So this is the idea for our question. We have got 12 poles there. All right. Then 4.22, the useful flux per pole. The useful flux per pole. The only part that we have, guys, that consists of this useful flux per pole is from where? Our EP, induced EMF that we have per phase. That is where we have got the useful flux. Remember that from E, remember this formula. We talked about this, guys. Our induced EMF per phase is going to be 4F. The useful flux that we have, therefore that is the one that we are considering. Then we must have TP, must have KF, we must have our pitch factor, our distribution factor. So this is the part that we are referring to. We can make this the subject. We simply have to divide this term by what we have on the right-hand side. This will be our consideration. So meaning to say our useful flux per pole is going to be what? AP over what? Now divide by 4, frequency, TP, all right? Our form factor, our pitch factor, and our distribution factor. So the question is, are we having these? Remember EP, our phase value, we calculated it here from the star connection that we are given. So it's there. The frequency is already given. Our TP, this one, are we having TP in this case? All right. From the information that we are given. All right. TP we do not have. So meaning to say we're going to calculate or we're going to be forced to calculate that TP. So that is the part that is going to carry all these marks. the calculation of that TP. Turns per what? Per phase. Because all these codes, they're there, KP, KD, or KF. But this one is not given. We do not have what? TP. So let's think about calculation of what? TP, guys, which is our turns per what? The turns per phase. So the turns per phase, I talked about this also before, that we can calculate if, let's say, we have the Z, which is what? Conductors per phase. Let's say that part is there. TP was going to be calculated from there. All right. So we're going to calculate TP from there. Conductors per phase over 2. But we do not have conductors per phase. To have the conductors per phase, we are talking about conductors, guys. Conductors per phase. It means we must have total conductors over total number of phases, which is number of phases that you are given. So we're going to need that ZP. From where? The total number of conductors. So we're going to need total conductors over what? Number of what? Of phases. We have the number of phases, but we do not have this. We have this one, but we do not have this one. Z total is not there. The total number is there. It's not the given. For us to have the total number of conductors, there is supposed to be a statement that consists of this. There's supposed to be a statement that consists of what? Conductors, somehow. So where can we have it? Let's just try to figure out with what we have here, because it's now gonna be stuck here. All right, let's check. Do we have in this case? All right, in this case, guys, we are going to need Z total to find ZP. If, let's say, we have got the total number of slots, because there we've got the number of poles that we are given, which is 12 poles. All right. Let's get some of the information here. Did I put all this information? Something that I need. There's something that I need that I see that I left here. All right. It is exactly here. I see it here to say there's something here. The stator has 3 slots per pole per phase and 20 conductors per slot. So it is important that when you take your information, guys, take everything. All right. So we've got the first part, 3 slots per pole per phase, our N. All right. Remember that small letter N is 3. That is slots per what? Per pole per phase. So that's your N6, guys. It's going to be like that. You have to take information. And there's this statement here, this one. Mostly you're not given, but this time it was given, this one. 20 conductors per slot. I was looking for this statement. We are given number of conductors. Let me just write in short. Number of what? Conductors. Number of conductors per slot. It is given 20 conductors per slot. All right. This is it. Let's get to the statement, because here we'll understand each other, guys, now because of this information. I was like wondering. Okay, let's check also if there's anything that is missing, because, all right, this one full. Talked about this distribution. All right, everything is fine now. All right, so let's go back here. This is the statement that I need here. To find our Z total, because we're talking about conductors, look for a statement Look for a statement that consists of what? Conductors inside. Do we have a statement that is conductors inside? It is there here. They are saying we are talking of number of conductors per slot. There are 20 conductors per slot. 20 conductors per slot. Per means what? Let's go to that per. 20 conductors per slot. What we need is the total conductors, total. So we must get rid of this pair. That is why they gave us this one this time. We just need to get rid of per slot, this one, per slot, per slot. Per slot that we are given. Meaning to say, we are going to need the number of what? The number of slots. That is the condition. So to have Z total, we are going to formulate. You see, guys, information, you don't just write a formula from nowhere. There is information that you have. Yes, you adjust the formulas that you have, that you've been given in your textbook to the information that you're given. Exam is something else, guys. So we're given conductors per what? Per slot. So that's our Z total can be calculated because we are simply saying our Z total will be what? Total conductors. We need total what? Conductors. So we are going to need total number of what? Of this one. This one that we are given. It's what? Conductor per slot. This one is conductor per slot that we are given here. But we need to get rid of what? Per slot. So how do you get rid of that per slot? You multiply by total number of slots. So you're going to multiply to the total number of slots. That is the idea. So in this case, the conductor per slot is the one that we are already given, the 20 there. Are we having the total number of slots? That is the question now. The total number of slots we do not have. We are given n slots per pole. So the total number of slots can be calculated by removing per this. We can calculate that one. So let's calculate this first. Total number of slots. So let me just calculate it this side. So you see, how do you connect your formulas, guys? It's just going to be like that. It's an electrotechnics, guys. All right. So let me just write it here. Total number of slots. Figure out a statement. Figure out from what you are given where slots is. And we have it here. Here. Slots per pole per phase. We just need to remove that. So it's simply, we're going to take our n as it is 3 slots per pole per what? We remove by what? Multiplying to remove per pole, number of poles. Meaning to say we are talking of what? The total poles. Times what? To remove per phase, number of phases that you have. Number of what? Phases. That is how you remove it. So n is that one that you are given, that you want to remove the slot per what, so that you remain with what? There's the slots. So it is going to be 3 times the total poles. In this case, we have, remember we calculated here from that first question, we said we've got what? 12. So there are 12 poles times, we have what? Number of phases. Remember, it's a 3 phase. So times 3. That was going to give us the total of 108 slots. So we've got 108 slots. That's the total number of slots. So using this conductor per slot concept that we are given to say, how many conductors are we going to have? We are saying there's 20 conductors per each slot. 20 times how many? Total number of slots, which is this one. So 20 times what? 108 was going to give us the total conductors, just like that. So we have our Z total, guys, from there. That was going to be 2,160 conductors. So we have got 2,160 conductors, total conductors, the total of them. This is our total. Number of conductors. Where is it needed to find conductors per phase? So conductor per phase was going to be calculated because we have our Z total, 2,160 conductors over how many phases? 3 phases total. The number of phases that we have is 3. So divide by 3, we're going to have what? 720. Remember, these are conductors, 3 phase. So it's conductor per phase that you're having there. That's our conductor per phase. So that's what we have there. Which we need where? Here, TP. To calculate that TP. So we're now just reversing. Remember, guys, those technique of reversal. So let's reverse. We're going to calculate our TP. So you're going to write your formula. TP is equal to this over this. We already have this. 720 over 2. So from there, you're going to have TP, tens per phase. So that was going to give you 360 tens per what? Per phase. You have your your TP, the tens per phase. So with that, we can use it to calculate what? That is the part that was missing on our formula. The useful flux per pole can be determined by substituting these values. Remember, guys, what you were having here. So your EP is there. Remember from that star connection, we have our induced EMF per phase of 2078.46. All right, everything over 4 times the frequency. Remember, that's 50. So you're just going to substitute our values. Everything is now there. 50 times the TP. That is the part that we have been calculating. All this part, it was for us to have the TP, the tens per phase. So that's 360. We have this value that is 360 times. Our form factor, as I said, if you're not given, you use what? 1,11, as we had, guys, even from our industrial electronics, for those who are doing industrial electronics and 4. All right. Our KP, pitch factor, remember, it's full pitched. So that will be 1 times your distribution factor you were given 0,96. So if you're not given, remember your formulas. So that was going to give us the useful flux per watt, per pole. So our useful flux per pole was going to give us 0,02709, something like that. In what? In Webers. You can even round off here to 3 decimal places like that. Or you can even convert to milliwebers by multiplying by 10 to the exponent of 3. The opposite. Remember, milliwebers is times 10 to the exponent of minus 3. So to convert to it, you multiply by the opposite. So the moment you multiply by 10 to the exponent of 3, your answer was going to be 27 here, point what? 0.09 milliwebers. This is just writing your final answer. You can just leave your answer there as it was. So that was the idea of the question. That was the idea of what? The question. So answer the question. Understand question. So these formulas, they can be manipulated depending with the textbook, guys, also that we are using. You can find different ways of expressing this induced EMF per phase. But like I said, I do not want us to have confusion. So I'm going to continue with this formula. We will try by all means to make adjustment until we have all these values that are on this formula, so that we do not have confusion of this formula today, another formula. So this is what we're going to use, guys, throughout for our revisions, as long we have to work with it. All right, then the other part here, it was to define the term distribution factor and 2 marks. So guys, I talked about the distribution factor on the introduction. The first one that I described there, it was because we were not given on the introduction. Like I said, guys, now I'm not going to write these definitions that we had on the introduction. So can we go through our introduction video? where we had these definitions. The distribution factor is the ratio of the actual EMF obtained to the EMF that would be concentrated in one slot only. In one slot only. So, like I said, let us go through those definitions that we had on the introduction video. It can help in your revisions, and join membership, guys, for more classes to come. So this is what we have for this question paper. Gonna meet again for any other revision, any other requests that we have. Let's communicate.